Hello, everyone. It's my great pleasure to present here. I think it's the final talk of this workshop with an application of the monitoring using seismic amino interferometry. In particular, I'm going to focus at underground hydrologic systems, which is also the topic of several very interesting posters in this week. Another key aspect of this study is that we not only look at the temporal changes, but also look at the spatial variations. This work was guided by my PhD advisors, Michelle, who is sitting here, also Robin Hust from MIT, and it's also in collaboration with a colleague, Alban Leconte from ISTER. In recent years, with the warming climate, big droughts have been plaguing numerous regions worldwide. This diagram shows that in the past 2 decades, over 1/3 of continental United States has been suffering from different levels of drought. This figure, upper one, shows the Lake Oroville in California at about full storage before a drought period, and almost nearing bone dry in 2014 during a drought period here. Now we're at another historic level of drought. Indeed, last summer we has witnessed severe extent of drought ravaging California and the southwestern United States. Together with the rapid growth of population, this drought is really bringing the water security to a tipping point. So if we think about the sources of fresh water, take California, for example, actually over 60% of the fresh water supply comes from groundwater in a dry year. So urgently needed now is the monitoring of both the structures and temporal behaviors of these underground aquifer systems. So, but as a seismologist, when California is mentioned, typically we would first think of all the earthquakes and faults, which means there must be or will be a lot of seismic stations. So those seismic stations are initially deployed for understanding earthquakes and tectonics, but it would be super if we can use them to deal with the drought, right? So in this talk, I'll show you a case study to explore how and to what extent can we use the seismic stations to deal with, to understand underground hydrology. So first, let's have a look at the typical underground aquifer structures. So this is a slice below the surface, looking at a few hundred meters. The tree here is not to scale. But it shows clearly the layer structures. We have this type of finer grains, mostly clay or silts. We also have the layers of coarser grains, mainly sands and gravels. So the the groundwater are mainly held in the pore space between the coarser grains of sands and gravels. So these layers are the aquifers. The aquifer layers are interbed between finer grain clays that bear very little groundwater. So how do we know how much water is stored in these underground systems? The most traditional way is to just drill a well and measure the hydraulic head or the groundwater table. But each well only measures the water table at a specific aquifer layer at one horizontal location. We don't know what's in between 2 wells. And those monitoring wells are so expensive to drill. It costs about $200,000 to drill a well at about 50 meters, and the price increases significantly at larger depths. So the spatial sampling of the well data is quite sparse. Moreover, the majority of wells in California are still being collected manually with once or twice samplings per year, meaning very limited temporal resolution. In recent years, GPS and INSAR have emerged as very appealing tools for hydrologic monitoring. And the idea is shown in this example. This is Senhua Queen Valley in central California, where the groundwater depletion has been excessive due to the heavy agricultural purposes. So on this picture, the signs on the pole shows the altitude of the land surface at different years. So you could see the ground surface was around here in 1925, but was around here in 1977. So it indicates about 9 meters of subsidence over half a century, which is quite dramatic. The mechanism for this dramatic subsidence is that the porous medium below the surface of the aquifers is acting really as a sponge soaked with water. Yeah, so it's the same as SpongeBob. By just measuring how much this sponge is squeezed or dilated, and combining some poroelastic modeling, they would be able to quantify the changes in pore pressure or groundwater level changes. This approach has really helped significantly for the hydraulic monitoring, benefiting from the good temporal resolution of GPS and spatial resolution of INSAR. I know Michelle said the temporal resolution of GPS was not good for tremor monitoring, but it's already much better for hydrologic monitoring compared to the well data. But the challenge with this type of data measured on the Earth's surface is that they lack the very crucial constraints for variations at different depths. And so in the end, what's typically people are interested in is the groundwater storage. But it's actually not easy to model the groundwater storage from displacement without knowing properly the aquifer structures first. There are also other remote sensing techniques, for example, satellite gravimetry, airborne electromagnetics, but they suffer from similar limitations. So what we hope to do here is to use seismic waves that travels in underground to add a new perspective to this hydraulic monitoring. To be more precise, we are measuring delta V over V, which is the relative changes in seismic velocity as a measure of elastic moduli and bulk density. So it can indicate the changes in hydraulic properties. I also want to note that delta V over V is essentially a mechanical parameter. It's often related to deformation, but not the same as deformation. Okay, so how to measure first the temporal changes? Thanks to Pela, who already introduced this, so I don't need to repeat. I just want to highlight that. So for monitoring applications, we typically use CODAR. With all due respect to Laurent, Pierre, and Francois, ballistic waves are not enough. We like CODAR because it's quite stable against the uniform distribution of noise sources. That means we don't need to stack the cross correlations over a long period of time, which gives much better temporal resolution. Also, the long travel path of CODAR allows us to detect very tiny changes in the medium property. With that said, many of you know that for monitoring applications, typically people only calculate the temporal changes, but the spatial variations are ignored. Because to use this formula, actually we assume that the changes are homogeneous. But as Pela just mentioned, just averaging and mixing everything together might cause troubles for interpretations. So here we go one step further from temporal changes to image the spatial variations in space. We do this by using this integration that connects delta V over V spatial resolution, spatial distribution, to the time shift measured at different lapse time. The kind of weighting function here is the so-called CODAR wave sensitivity kernels, which statistically describe the travel path of CODAR waves. And here is an example. Jocelyn and Ludovic have talked about this. I'm not going into details. And just to mention that the kernel we use here are based on radiative transfer equation. So it's different from previous studies using the kernels under diffusion approximation. Also note that here I'm using the 2D kernels, which mainly describe so we think it's mainly surface waves. Ludovic also mentioned that there is this new publication which takes into account the coupling between surface and body waves. It's just I haven't used that yet. But with this equation, we can invert for the dV/V spatial distribution by solving this type of inverse problem. Here, I just take the classic approach from this Tarantella formula. Also, sadly, I think this equation marks the last equation in this summer school. Here is to show you, so we can just repeat this type of inversion at consecutive dates. And here I'm showing you the space-time evolution of delta V/V from this measurement. So this is our study area in Los Angeles in Southern California. And we measure the space-time changes from 2000 to 2020. And on this movie, you can see a general change from bluish color to reddish color, meaning that the groundwater is declining over time. Right, so I also want to compare this type of space-time measurements with INSAR and GPS. So on this 2D plan with temporal resolution from low to high and spatial resolution from low to high, GPS excels in high temporal resolution, INSAR excels in high spatial resolution. And our space-time, delta V/V, falls around here, which kind of incorporates the advantages of both GPS and INSAR. So in the rest of my talk, I'll use this pilot application in Los Angeles to show you, examine the validity of our dV/V monitoring and imaging. Two, to use dV/V to aid in the understanding of underground hydrologic processes. So this shows our study area in metropolitan LA, comprising a number of groundwater basins. Mainly is this Santa Ana Basin and LA Central Basin. So these basins are mainly bounded by mountains and faults, but they are also partly partitioned by municipal borders. Oh, I need to note that each of these basins are adjudicated to a different local water department. So the groundwater in this area exhibits strong seasonal variability due to the precipitation in winters that recharge the groundwater system and the heavy well pumping in summers that depletes the groundwater system. Also, one thing that hydrogeologists already know about this area is that the northern east parts are mainly characterized as unconfined or forebay because it contains mostly the sand and gravel aquifers, whereas the southern west part is mainly characterized as confined zone. That means the aquifers are confined by a large number of clay lenses or layers. So you can see the compressibility of these two areas are quite different. For this confined zone, because of the highly compressible clay content, this is a part that acts as a sponge. But the unconfined zone doesn't really deform much. So to calculate delta V/V, we use about 50 broadband stations in Southern California. And we then divide this area into 2 by 2 kilometer pixels to invert for delta V/V at each pixel. Here on the right-hand side, the blue line is delta V/V averaged over all pixels in the study area. The vertical axis is plotted in reverse direction for a more intuitive comparison with groundwater. So now upwards means more groundwater and downwards means less groundwater. The gray line is a low-pass filtered version to show the long-term trend. And on the bottom, I plot the cumulative precipitation. So you can see the blue line and the gray line shows that over the past 2 decades, there is a decreasing trend on this line corresponding to the dearth of precipitation in this area. Also, this decreasing trend was interrupted by several briefly increasing episodes corresponding to years with some storms. Superimposed on this long-term trend are some short period variations. Those are associated with the annual hydrological cycles. So that plot before was averaged over the entire study area. Here, I zoom into one basin to look at some localized change. So the blue line, again, is dV over V, but only averaged within Santa Ana Basin. The yellow line with circles are the hydraulic head or water level measured at a local well. So you can see over the past 2 decades, the delta V over V and hydraulic head match very well with each other, both regarding the long-term change and the short-term changes. This is very encouraging because, because it means that we can probably use large number of existing seismometers in California or worldwide to as an alternative of the groundwater wells, which would be very promising because it would greatly improve the spatial and temporal resolution of in situ well measurements, while avoiding the expensive cost for drilling and maintaining groundwater wells. Okay, so so far we've been looking at the temporal changes. Now I'll move to spatial variations. Here, this map shows the seasonal variability of dV over V. So the color at each pixel indicates the amplitude of seasonal variations at this location. We obtained the seasonal amplitude by sinusoidal fittings. So reddish color means stronger seasonal variability, and bluish color means weaker. The dominant feature in this plot is that you can see the strongest seasonal variability concentrated in Santa Ana Basin, with this shape quite consistent with the border of the Santa Ana Basin. We also observe this sharp gradient along the boundary between confined and unconfined zone, which seemed to make sense. And now I'll further substantiate this dV over V mapping by comparing it to a deformation map inferred from INSAR. So on the right-hand side is INSAR measurement, which is, to be precise, the vertical displacement measured at surface, whereas our delta V over V is measuring the mechanical properties at depth. Despite being measuring different physical properties, these two maps show largely consistent features. Both have the most pronounced changes in Santa Ana Basin on the confined side. The main difference between these two is perhaps this part in LA Central Basin appearing on INSAR but missing on dV over V. So what's the reason for that? We try to answer this by thinking about one unique ability of our seismological approach. That is, we have this different depth sensitivity by using different frequency. So this map is measured within one frequency band. If I look at the results at different frequency band, from left to right are measured with decreasing frequencies corresponding to deeper and deeper depths below the surface. So you can see from left to right, this reddish area tends to move southeastwards, which means the aquifers seem to extend deeper southeastwards from LA Central Basin to here further in Santa Ana Basin. But consistently across these different depths, all the changes, dominant changes, concentrate on the confined side. If I display the INSAR map again, to some degree, you can see the INSAR is an integration of the changes occurred at different depth. So compared with INSAR, our delta V over V further offer the information of the depth or thickness of the aquifer layers, which can be crucial for decision makers to determine the optimal strategies for drilling and pumping to augment sustainable groundwater management. So in the last part of my talk, I'm gonna look at the long-term changes of delta V over V. So showing here are the accumulated dV over V from 2000 to 2020. The reddish color indicates a cumulative decline of groundwater, and the bluish color and cumulative increase. So what we can see here, the cumulative changes in different basins are quite different. In LA Central and San Gabriel basins, we see that there are much less water now than 21 years ago. But in Santa Ana Basin, it seems in the long term, the groundwater recovers even with a slight increase. What's particularly interesting to me is that if we look at these two basins, neighboring basins, the border between these two basins is a county line. It's a pure municipal border, so that means there is no natural barriers for groundwater flow. But we observe opposite signs of cumulative changes in these two basins. So what's the reason? We're trying to find out the answer by looking at the temporal changes. So this is the temporal dV over V averaged within Santa Ana Basin. If we look at a particular year, the total annual change is a balance between two main seasonal factors. That means the rainfall-induced changes in the winter minus the pumping-induced changes in the summer. And if I plot the relationship between these two components over all these years, here the horizontal axis represents rainfall-induced component, and the vertical one represent pumping-induced changes. So this scatter diagram shows that these two components really exhibits a linear relationship, and the red line is a best fitting line. What does that mean? That means when it rained more in this basin, they pump more. When it rained less, they pump less. So this way, in the long term, they manage to keep a balance of the groundwater storage. So this is the Santa Ana Basin, which is actually not the case for LA Central or San Gabriel Basin. As we can see, there is very little evidence of linear relationship. Furthermore, there are both more dots on the upper triangle corresponding to years when the pumping-induced changes exceeds the rainfall-induced changes. That means the years of overdraft. So the accumulation of all this overdraft leads to the long-term axis of groundwater decline. So this example shows that the different pumping strategies is most likely the reason for the different signs observed in these two adjacent basins. And it shows that anthropogenic activity can play a significant role in shaping the near-surface systems, compounding the effect of climate change. This type of analysis also shows that dV over V can be a new way for assessing groundwater budgets at a basin-wide scale. So this measurement, this way is independent from the traditional way based on stream flow, precipitation, or hydraulic tide measurements, which actually subject to high uncertainty without a good model of the aquifer structures. Okay, to conclude this LA pilot study, so we show that we can measure the space-time evolution of delta V over V, and this measurement is validated by the hydraulic tide for the temporal changes and INSAR for the spatial changes. Also, compared to the traditional measurement from geodetic technique, we further characterize the hydrology at different depths. In addition, based on the spirit from science to solution, from knowledge to action, data view over V can be a new independent way for assessing groundwater storage and management. To look forward, we see that the space-time data view over V can be a very powerful geodata set for a lot of objectives in long-term monitoring because it's advantageous in different aspects. Here I show a brief comparison of data view over V and INSAR. You can see they really excels in different aspects and can be really complementary to each other. That brings me to a longer objective. It's absolutely fascinating to look at the Earth's cores, but we can also use seismic interferometry to add new insights to near-surface processes related to environmental problems or assessing the role of human activities on the shallow subsurface. Thank you.